Alright, welcome to this video where we are going to talk about periodic trends. And as you can see, I'm standing in front of the periodic table, and there's a lot of patterns that occur within the periodic table. We've already talked about core charge, valence electrons, properties, but there's a lot more to that. And so what's really cool about the periodic table is that the periodic table was actually set up the way that we see it today, in a pretty close to similar fashion as it is today. And it was set up in this way before we knew about a lot of these trends. And so it's just something really interesting. And so the periodic table, because it has these trends, it has a lot of predicting power to it, to where we can predict certain properties and certain characteristics of different elements. And so if you remember this particular chart here, this chart is your practice problem from the previous Ed puzzle. And if you take a look, it was calculating the core effective nuclear charge. Now, if you look here, you can see that hydrogen has an effective nuclear charge of 1+. And then lithium has a 1+, and sodium has a 1+. And again, what that means is this outer electron right here, even though lithium has 3 protons in there, it only experiences a 1 positive charge because those 2 inner electrons are shielding the nucleus. Now, if you take a look as you go from left to right, you'll see that the effective nuclear charge increases. So effective nuclear charge increases as you go from left to right. As you go from top to bottom, though, you see that it actually stays the same. And so hydrogen has a 1+, lithium has a 1+, sodium has a 1+, and so on. Now, something to keep in mind is we want to keep in mind 2 things. We want to keep in mind that the electron is attracted to the nucleus because of the positive charge. But that strength of attraction is also dependent on the distance. So hydrogen, lithium, and sodium, they all have a 1+ charge, but as the electron gets farther from the nucleus, the force of attraction is going to decrease. And so if an electron is farther from the nucleus, it's going to have a smaller force of attraction. If an electron is around an atom that has a larger effective nuclear charge, it's going to have a larger force of attraction. So if you take a look at boron and carbon here, for example, this particular electron and this particular electron, if you consider those 2 electrons, well, this first electron and this second electron are on the same energy level. So they're about the same distance. So we'll learn it's a little bit not true later, but they're about the same distance. And so this right here, however, is only attracted to a 3 positive charge. This, however, is attracted to a 4 positive, and so that makes the carbon have a stronger force of attraction. And so if you take a look, as you go from left to right, what you want to think about is, notice how the effective nuclear charge increases, and so the force of attraction to the valence electron increases as well. So generally, from left to right, the force of attraction for those valence electrons to the nucleus increases. So it's something to consider. And then when we go from top to bottom, the force of attraction decreases. So that's what you want to think about. You want to think about that force of attraction when we're talking about these trends. So as the effective nuclear charge increases, the attraction for these electrons increases as well. And so this is what I just said here. And if you, we're going to take a look at this chart again. So again, as the effective nuclear charge increases, goes 1, 2, 3, 4, 5, 6, and so on, what ends up happening is the force of attraction increases. So there's a larger force of attraction for neon compared to lithium. Now, an increase in the number of energy levels, however, will increase the distance of the electron, which decreases the force of attraction. These 2 first sets of these 2 lines here, so increase nuclear charge and increase distance, those are going to be the 2 factors that affect most of these trends. So let's go ahead and take a look here. So full energy levels provide some shielding from the pull of the nucleus and increase the radius. And so this is something that we have talked about. So what that means is the inner electrons will provide some sort of shielding of the nucleus to where the outer electrons do not experience all of the protons that are in the nucleus. So again, if you, for example, you take a look at sodium here, sodium has 11 protons. However, we have 10 inner electrons here. There's 10 of them. And those 10 inner electrons shield the nucleus from this one valence electron. Now, atomic radius refers to the distance between the nucleus and the outer edge of the electron cloud. It is influenced by the effective nuclear charge and the number of energy levels. So there's two things that affect atomic radius: effective nuclear charge, which we'll talk about in a moment, and then the number of energy levels. And that makes sense because as we add more energy levels, it's going to get larger. And so you can see going down, it's going to get larger because there's more energy levels. Now, as we go from left to right, we're going to learn that the atoms, even though they look the same on the picture, they look about the same size, the atoms are actually going to get smaller going from left to right. And that's actually something that's interesting and different. We'll talk about that in a moment. Now we have ionization energy. All right, so ionization energy refers to the energy required to remove an electron. Now, the electron's attracted to the nucleus, and so to remove that electron, you need to apply some amount of force to it, and you need to put some amount of energy into it to remove that electron. So think about magnets. If we have two small magnets, it's going to take some sort of energy to separate those magnets. But let's say we have two large magnets. It's going to take more energy to remove those magnets from each other. And so thinking about the energy required to move this electron, again, this electron here is attracted to the nucleus. This electron will require less energy to remove compared to this one. And the reason why is because this electron is attracted to a 2 positive charge. This is attracted to a 1 positive charge. So beryllium is going to require more energy to remove that electron. So beryllium will have a higher electronegativity. Ionization energy. It has a larger ionization energy. Lithium and sodium, though, if you take a look, lithium and sodium, well, lithium has a 1 positive, sodium has a 1 positive, so the effective nuclear charge is the same. However, sodium's electron is farther from the nucleus, and lithium's is closer, and so it's going to require more energy to remove lithium's electron. In general, overall, ionization energy will increase as you go up the periodic table because the electrons get closer to the nucleus, and it will increase going from left to right because you're increasing the effective nuclear charge. All right. However, an exception to this ionization energy does occur between groups 2 and 3. All right. So I just said that ionization energy increases left to right because there's an increase in effective nuclear charge. And let's go ahead and take a look again. So again, ionization energy increases as you go from left to right because the effective nuclear charge is increasing. However, there is an exception when you go from group 2 to group 3. And the reason why that is because the p orbitals don't penetrate the nuclear region as much as the s orbitals do. And we're going to take a look at that here in a moment. And so the nucleus doesn't hold on to p orbitals as tightly. So if you take a look, you can see, looking at the shape of these orbitals, you'll see that the s orbital, the nucleus definitely holds on to those to the s electrons more tightly than the p orbitals. You can see here in the middle, the p orbital actually has this region where the electron isn't really occupying, and so because of that, even though there is an increase in effective nuclear charge, when you go from the second to the third, column to the third column, there's a decrease in ionization energy, which is because of that. There's actually another exception as well for ionization energy. And an exception occurs between the 5th column and the 6th column. And so the reason why that is because in the 6th column there is a pairing of electrons that occur. And electrons don't like other electrons, and they repel each other. And so that pairing of electrons causes the electrons to repel each other, which, even though there is an increase in effective nuclear charge, there's going to be a decrease in ionization energy because those electrons are repelling each other. And so if you take a look here, this is an example of what I'm talking about. So nitrogen has an effective nuclear charge of 5, and oxygen has an effective nuclear charge of 6. And so, but even though oxygen has a larger effective nuclear charge, this electron right here is actually easier to remove than this electron. And the reason why it is because of this pairing that occurs. When the electrons pair, they repel each other. That electron-electron repulsion causes it to be easier to remove this electron here because of that repulsion, even though oxygen does have a larger effective nuclear charge. All right. The other thing, too, is when you remove an electron, it requires a certain amount of energy. If you remove a second electron from the same element, it'll require more energy to remove that second electron than the first one. And the reason why is because when you're removing that first electron, what you're doing is you're decreasing the number of electrons, but keeping the protons the same, so the proton to electron ratio changes to where you have more protons than electrons, which means that the protons are holding onto those electrons more tightly. And so the point here is that if you remove a second electron from an element, it's going to require more energy than removing the first one. If you were going to remove a third one, that third one will require more energy than the second and the first one. And so if you were to remove an electron from a lower energy level, it will require a significant amount more energy. All right. So what that's pretty much saying here is think about like boron here. So boron can lose these 3 electrons. And so if we think about the energy it takes to remove, let's say, this electron, well, the energy to remove this second electron will be more than the energy required to move this one. And then the energy required to move the third electron here will be greater than the other 2 as well. Now, let's think about lithium. If we have lithium here, we move this electron, takes a certain amount of energy, but if you remove a second electron, notice how you're removing it from a lower energy level. And that actually, when you remove it from a lower energy level, it requires a significantly larger amount of energy, like a very, very noticeably larger amount of energy. So the point here is that, so if we were to move the 2 electrons from beryllium, there is an increase from one to another. However, if we were to move 2 from lithium, there is a greater increase because that second one is coming from the lower energy level. Now, there is an increase in ionization energy to remove electrons because of this proton to electron ratio. And so that's what I just talked about a moment ago. So when you're removing a second electron, there is an increase because you have a increase in the proton to electron ratio. You have less electrons, same amount of protons, so it creates a larger force of attraction. Now there is, again, this is what I just talked about, there is an exceptionally large increase in ionization energy between energy levels. And so when you take valence electrons away, they require energy, but then when you start taking inner electrons away, it requires a lot of energy, a very, very large amount of energy. And part of the reason why is because those electrons are closer to the nucleus, and there's less shielding on those lower energy levels. Okay, electronegativity. So electronegativity has to do with sharing electrons. So ionization energy has to do with removing electrons, but we're going to learn later that some elements will share their electrons with other elements. And so the electronegativity is a property which measures the attraction of an atom for a pair of valence electrons that's shared between another atom. And so when atoms start sharing electrons, when we start talking about that, one atom is going to have a larger electronegativity, so it's going to pull those shared electrons more. So it's going to have a larger pull on those electrons. And we're going to learn about this more in the future, but it's going to essentially make an uneven sharing of electrons. And the idea of electronegativity is the same as the idea of ionization energy. As you go down, what ends up happening is these valence electrons are farther from the nucleus. So as you go down, the force of attraction decreases, which means that they have a smaller electronegativity. So as you go down, there's a smaller electronegativity because the electrons are farther from the nucleus, so the nucleus doesn't pull the electrons as much. Now, as you go from left to right, notice how there's an increase in effective nuclear charge, which means there's an increase in attraction, which means that there's an increase in electronegativity, because as you increase effective nuclear charge, as you increase attraction, you're going to have those nuclei pull harder on those electrons that they're sharing. All right. Ionic radius is the distance from the nucleus to the outer edge of the electron cloud of an ion, though. And so we're going to talk about an ion here in a moment, but essentially it's the same thing as atomic radius. However, we're going to learn that atoms tend to either lose or gain electrons, and when they lose or gain electrons, they become ions. And so metals will tend to lose electrons. So remember the staircase right here. So here's the staircase, and everything to the left of the staircase is a metal, and those tend to lose electrons. Now when they lose electrons, they're actually losing an entire energy level. And we're going to look at some examples of this in class, but when they lose electrons, they're losing an entire energy level. And so what ends up happening is they get smaller. So they get smaller when they lose that energy level. It's kind of like removing a layer of onion. It gets smaller. Nonmetals tend to gain electrons. So here's the staircase. Nonmetals tend to gain electrons. So these tend to gain electrons. Now, when they gain electrons, the atoms actually get bigger. So when they gain electrons to become ions, they actually get larger. And the reason why they get larger is because you are adding an electron to an electron cloud. Electrons don't like electrons, so they kind of spread out more. So they push each other away and they spread out more. And so what ends up happening is when you add an electron, the electrons kind of push each other away and it fluffs out a little bit. And so when atoms gain electrons, they get larger. When atoms lose electrons, they get smaller. And so here's a chart that's in your book. You'll see here that notice how the right represents the atom. All right, so this gray represents the atom. And notice how the ion here, when it loses an electron, notice how it gets quite a bit smaller. So notice how it gets quite a bit smaller. This here, if you take a look, notice how, again, it's going to be the atom, and then when it loses its electrons, it gets smaller because it's losing that whole energy level. Now on this side though, notice how this is the atom. So now this is the atom, but when it gains electrons, it actually gets larger. So when it gains electrons, it gets larger. And the reason why it gets larger again is because those electrons are pushing each other away. And so the point here is if atoms lose electrons, they get smaller because they're losing a whole energy level. If they get larger, they get bigger. If they gain an electron, they get bigger because the electrons are pushing each other away. Now, when considering ions, when atoms lose or gain electrons, you can have different atoms that will, let's say, lose electrons. And in fact, if you think about these two right here, if they lose 2 electrons, if magnesium loses 2 and sodium loses 1, they will both end up with 10 electrons. If they end up with 10 electrons, and you think about electron configuration, if they have 10 electrons, they'll have the same electron configuration. Because magnesium has 12, it lost 2. Sodium has 11, it lost 1. And so they both end up with 10, and so they have the same electron configuration. So those are said to have isoelectronic configurations. And so let's go ahead and take a look at this. So we're gonna talk about the charge here later, but notice how oxygen, when oxygen is in its normal electron configuration, it's 1s2, 2s2, 2p4. But if it were to gain 2 electrons, it would then have it would be gaining it in the 2p's, and it would be 1s2, 2s2, 2p6. Now magnesium, notice how magnesium is 1s2, 2s2, 2p6, 3s2. But if magnesium loses 2 electrons, it'll end up being 1s2, 2s2, 2p6. And notice how this electron configuration and this electron configuration are the same. So I did want to finish with a summary here, and what I want to talk about is I want to talk about atomic radius specifically. And when we're looking at atomic radius, I want you to look at the gray part of the atom. So again, or the gray part of these models here. So the gray part is the atom, and the colored part are the ions. So let's not look at the colored parts, just the gray part. And so the gray part, I want you to notice the size. As you go from top to bottom, look at the size of the atom. Notice how it gets larger. And the reason why is because it has more energy levels. But notice what happens to the size of it as you go from left to right. Notice what happens, how the size actually gets smaller. And you can see the numbers right here. So it goes 1.34, 0.9, 0.8, 0.73, and 0.71. So you can see that as it goes from left to right, it gets smaller. So why would it get smaller going left to right? Because if you take a look here, if you take a look at boron, boron is 0.82, but fluorine is 0.71. So how is it that fluorine has more electrons, more protons, but it's smaller? And the way you need to think about it is, first off, you want to realize that as you go from left to right, the attraction between the nucleus and the electrons is increasing. And we want to think about the nucleus like this ball here. And so if we think about the nucleus like this ball, this sort of, forget what they're called, stress balls, there we go, stress ball. If you think about it, if there's a larger force of attraction, if you think about the electron around the nucleus here, and you think about the nucleus in the center, and there's a stronger force of attraction. If there's a stronger force of attraction, what ends up happening is the atom squishes, the electron cloud squishes because there's a larger force of attraction. What if there's a smaller force of attraction? Well, what ends up happening is it's not so squished. And so even though this has more electrons and more protons, it's going to be smaller than this because there's a larger force of attraction between the electrons in the nucleus. The same thing from aluminum to chlorine, and actually across the whole periodic table here. And so as you go from left to right, there is an increase in the force of attraction, to where as we increase the force of attraction, the electron cloud gets more compressed. So it kind of gets squished. And so just wanted to really emphasize that. So as you go from left to right, gets squished more. So just wanted to add that in there. The other thing too is think about electron attraction to the nucleus increases going up. It increases going up because the electron's getting closer to the nucleus. It also increases going left to right, because as you go from left to right, there's an increase in effective nuclear charge. And so that's the main thing you want to remember, that there's an increase in electron attraction between the valence electrons in the nucleus going up, and there's an increase in electron attraction going from left to right because there's an increase in core effective nuclear charge. And so that means that there's an increase in ionization energy, which is the energy to remove an electron. There's also an increase in electronegativity this way, which is the pull on shared electrons. And so increase in ionization energy, increase in electronegativity as well. And that is going to be it. So we're going to practice this a lot in class. And again, the key thing is you have to think about electron attraction. All right. You guys have a great day, and come with questions. Take care.